Within the eastern United States, we don't often think about glaciers or deserts. However, I find those areas to be some of the most beautiful places on the planet. And even when there are no more glaciers, such as in this photo here, we still see these broad U-shaped valleys which indicate that glaciers were there. And then there are places like this, which is a desert or close to a desert environment today, but it also has rocks that represent more extreme desert conditions in the past. So let's start with the cold. Glaciers are flowing masses of ice. However, it's not as simple as a snowflake directly turning into a glacier. Instead, each individual snowflake sort of loses its shape and it turns into granular snow. That granular snow solidifies into something called firn, which is basically a bunch of little particles of ice. Eventually that firn will be consolidated into a glacier. Now there are two major types of glaciers based on where they occur. Ice sheets occur on continents, whereas valley or alpine glaciers occur in mountainous areas. Currently there are only two ice sheets on Earth. There's the large one over Antarctica and there's one over Greenland. In the past, there have been ice sheets over North America, over Europe, over parts of Asia as well. Mountainous glaciation occurs any place where there's a combination of altitude or high latitude that allows glaciers to build up. And there's a lot of minor types of glaciers, especially associated with mountains. Now, in general, the motion of glaciers is going to be the same whether it's an ice sheet or an alpine glacier. All the movement is away from the center of accumulation. Now that movement can happen in a couple different ways. There's movement at the very bottom where the glacier slides across the surface. That's called basal slip. And then there's the internal flow section. It's called plastic flow. That plastic flow section allows movement because the ice is under enough pressure from the ice above it. And so instead of breaking, it allows the ice to be deformed plastically. Now at the very top is a zone of fracture. And within that zone of fracture, you don't have the same kind of pressure. That means when the ice moves, instead of deforming plastically, it deforms in a brittle way, forming these deep crevasses. Now, glaciers don't tend to move very fast. They tend to move a few feet, 6 to 10 feet per day. However, there's a large amount of variation. And even within an individual glacier, there can be short surges. These surges often occur when there's melting of glacial ice. That water moves to the bottom, moves underneath the glacier, and that glacier can slide very quickly along that lubricated surface. So when we look at glaciers are always moving. So the ice within a glacier is moving, and the ice is going to be moving downhill regardless of whether or not the end of the glacier is moving downhill or it's moving uphill. So what we just saw was an instance where the amount of accumulation exceeded the amount of wastage. So accumulation is all the snow, all the water that's flowing onto the glacier and then freezing. The snow line separates the accumulation zone from the wastage zone. The wastage zone refers to the area where there is melting and where there is sublimation, where ice is transforming directly into a water vapor. Now, if you look at a glacial retreat, we can see the front edge of that glacier is slowly moving uphill, but the ice is still moving downhill. So in this situation, the amount of wastage exceeds the amount of accumulation. So this is known as the glacial budget. In addition to the rather slow process of melting and sublimation of ice within the zone of wastage, we can also have ice break off in massive pieces. So that's called calving, and that's going to be the origin of icebergs. As ice moves across the land surface, it erodes the earth in two different ways, and these two ways work in conjunction with each other. One is by plucking. So it's picking up pieces of rock, pieces of whatever is on the surface. And it can use these rocks to scratch the surface, causing abrasion. And that abrasion then loosens up the surface to allow more plucking. So as a result of glacial abrasion, we have two different kinds of environments, two different specific examples shown here. One is rock flour. As you grind up rock, you can create pulverized rock, very fine-grained sediment. The picture in the lower left shows two streams coming together. The stream that's cloudy has a high amount of rock flour. The stream that's very clear is not coming from a glacial area. On the right side are very wide glacial striations. These are grooves in the bedrock caused by the dragging of other rocks across the land surface. These particular ones are in an island just offshore of Ohio, and these are very broad, so these are on the scale of a human. Now, in addition to these small features like glacial striations, glaciers can have some big impacts on the land, especially in mountainous areas. So here we have an area that's been heavily glaciated. We can see a glacial trough, this broad U-shaped valley formed by a glacier. When you see a valley, you can quickly decide if it's been formed by a glacier or a river by looking at the shape. River valleys are going to have a V shape. Now, glacial troughs have to start somewhere in mountainous areas. That very beginning of a glacier up in a mountain is called a cirque. And when you have two glacial valleys side by side, it forms a sharp edge called an arête. When you have three or more cirques come together, that's going to be a horn. And inevitably, you'll have some glacial troughs truncate other glacial troughs. That's going to cause hanging valleys, as well as truncated spurs, which is an arête that has been cut off. Now, in addition to eroding materials, glaciers can deposit. So glacial drift refers to any kind of sediment that has a glacial origin. And there are two types. One is till, which has to be deposited directly by the ice, and the other is stratified drift. It's deposited by glacial meltwater. So in this photo on the lower right, you can see a person standing next to this massive rock, which was deposited by a glacier. You know instantly that this is going to be till and not stratified drift because glacial meltwater is not going to be able to move something that massive. There's a couple different categories of landforms made by till. The most common that you'll see are moraines, which are layers or ridges of till. Within this image, there are lateral moraines, which form on the very edges of these alpine glaciers. And these are areas where the glacier is rubbing up against the side of the mountain. So it's scraping off some of the rocky material. Eventually, two different alpine glaciers can come together. And that means these two lateral moraines are going to come together and form a medial moraine. And there are other kinds of moraines as well. Anytime a glacier is hanging out in one spot, remember the ice is still moving even if the edge of the glacier is not moving. That means material is being deposited in one spot. An end moraine is any kind of deposit of till that's being formed at the end of a glacier. And there are two types. The terminal moraine is the end moraine that is the farthest the glacier ever went. A recessional moraine is any intermediate moraine, so it just hung out in a spot for a while before it receded later. Ground moraines on the bottom refer to the till deposits that cover an entire surface. Now there are a few other smaller features made of till, such as drumlins. Now these are rather small hills, and in this case the steep side of the hill will face the direction from which the ice advanced. In this particular case, we can see that the ice came from the right side. Kettles are commonly expressed as lakes today, and they were formed by ice being buried within till. Eventually that ice would melt, and it would form a depression within this larger body of till. Cave refers to sediments deposited usually on top of a glacier, but sometimes within a glacier. This happens because glaciers are moving and they're made of ice, but they can also have small streams on top of them or even within them. Some of these streams are going to cause eskers. these very elongate snake-like mounds of sand. Now, stratified drift doesn't look nearly as interesting as some of these massive moraines, and it doesn't cause these massive features like arêtes and horns. An outwash plain occurs whenever you have meltwater coming off of an ice sheet. A valley train is basically the same thing, but it's coming off of a valley glacier or an alpine glacier. In both cases, you have an area that's dense with braided streams. So you have a lot of water, a lot of sediment, a lot of very fine-grained sediment over a very extensive area. Now let's switch gears here and start talking about the opposite extreme. Instead of cold, let's talk about hot. Dry lands cover about a third of the Earth's surface and are commonly divided into deserts and steppes, steppes being semi-desert, semi-arid areas. But the real question is, how dry is dry? And I'm glad your textbook talked about this a little bit. However, it came down to a definition of the water balance. It's the amount of precipitation less than the amount of evaporation. Well, that's a pretty good definition of a desert, and that's probably the most common one. However, it's not the only one, and it's not perfect. And that's because there are some places where you have lots of evaporation, and in fact that evaporation can exceed the amount of precipitation. That means there are some tropical areas which, by the definition set in your book, would actually be considered a desert. Okay. From a more practical standpoint, most people in the United States have an arbitrary level of 10 inches. If it's less than 10 inches, we call it a desert. From the international perspective, most people would say 10 centimeters. And this is in part because there are a lot more dry areas outside of the United States, so that minimum threshold is a little bit lower. When we look at where dry lands of the world occur, hopefully you'll notice a couple different patterns here. One is that we have low latitude deserts. Low latitude meaning that you have deserts occurring at about the Tropic of Capricorn, the Tropic of Cancer, close to 30 degrees north latitude and 30 degrees south latitude. In those cases, this is because you have air coming from high elevation down toward the surface. That high elevation air is very dry and very cold. When it moves down to the surface, it warms up, and not only was it dry to start with, it now is warming up, meaning that it can absorb even more moisture. So if you look at the Sahara and the Arabian Desert, those are right at about 30 degrees north latitude. If you look in the southern hemisphere, the Great Sandy and Simpson Deserts in Australia are also at about 30 degrees south latitude. The mid-latitude deserts, the ones that aren't within those bands, such as the Turkestan and the Gobi deserts, those tend to be very far from coast. In particular, they tend to be very far from an east coast. So because of the atmospheric circulation patterns, by the time any air mass that has been near an ocean gets to them, it's already dumped out all of its water. So that explains the Turkestan and the Gobi Desert. If you look at a few others, you can see the Great Basin and Sonoran Desert in North America, the Atacama Desert in South America, the Namib and Kalahari in South Africa. And these are around 30 degrees north and south latitude, but more importantly, they're located where the circulation patterns force the water out of the air because of a mountain range, and then they get over the mountain range and the air is then dry. So there's three main reasons why we have dry lands on Earth. So within deserts, we don't think of water as being very important, but actually water is the major agent of erosion even in deserts. It may be a flash flood, but it still moves a lot of stuff. However, what's unique about deserts is that wind erosion, unlike in other environments, is also fairly significant. But again, not as important as water even in deserts. There are two ways that wind erodes materials: deflation and abrasion. In the case of deflation, you're simply blowing things out of the way. In the case of abrasion, you're picking up those things, picking up that sand, and blowing it against something. So just like glaciers could pick up materials and grind it against the Earth's surface, wind can pick up sand and use it to grind against surfaces. So two examples here of deflation are a desert pavement at the top and then blowouts at the bottom. In the case of desert pavement, you have a combination of sediment sizes, very small stuff, and you have larger particles. That small stuff is being blown away, and eventually you're only left with those big particles that are too small to be moved by the wind. So this rocky surface is desert pavement. In the bottom, blowouts form when you have a lack of vegetation. Here you see a couple mounds that are resistant to deflation because they have vegetation. Now in the case of abrasion by wind, there's a lot of different names for some really bizarre features. In general, there are two common terms that you may run across. The more common one is on the lower right, a ventifact. Vent meaning wind. So ventifacts form usually very near the surface, and these are individual rocks that are sculpted by the abrasion of wind. Yardangs are not nearly as common. Instead of being isolated rocks, they tend to be elongated ridges, almost like if you took a boat and flipped it upside down. So that was the erosive power of wind. Now let's look at the depositional ability of wind. There are two main categories of materials that can be picked up by wind: silt and sand. In the case of silt, when it's blown into large blankets, large deposits, it's called less. And we have massive amounts of less in the central United States, which is one of the reasons why the central United States has such phenomenal agriculture. It's because we're planting within less. There's a couple other places that have very thick deposits. Central China and then the Ukraine. In the case of China, the less deposits are a little bit different. They're from a different origin. In the case of Ukraine, they're actually similar to the deposits here in the United States. And that's also why the Ukraine has been called the breadbasket of Europe. It's also a very agriculturally rich area. When sand is being blown into piles, it's called dunes. And the type of dune will be determined based on the number of wind directions, the amount of sand, and whether or not there's any vegetation. There are three types of dunes shown on this slide. They're similar in that they all form with wind in one direction, and in none of these cases is there any significant amount of vegetation. The difference is just about the amount of sand that's present. In the case of Barken dunes on the upper left, there's a relatively limited amount of sand. In that case, you form isolated dunes. In the case of transverse dunes, you have an abundant amount of sand. So instead of these isolated dunes, you have elongated ridges. Barkenoid is in between, where you have a moderate amount of sand. Instead of isolated dunes, you have dunes that kind of curve into each other. So you have this curvy surface instead of the straight dunes that you have in transverse. So in this slide, you have the transverse dune again in the upper left. Wind is moving in one direction. There's a lot of sand. There's no vegetation. A longitudinal dune on the upper right can have a lot of sand. It can have a little sand. The key is that there are at least two different directions of wind that are not directly offsetting each other. In other words, the sand is being pushed to one side, then pushed to another side, then pushed to another side. So you form ridges of dunes, but those dunes are perpendicular to what we would expect to see in a transverse dune. In a parabolic dune, wind is moving just in one direction, and there is abundant sand, but the key difference here is that there's vegetation to hold some of the dune in place. One of the rarest types of dunes is on the lower right. This is a star dune. In this case, you have a lot of sand, but wind is moving from 3 or more directions depending on the time of day or the time of the year.